In this episode, the largest structure ever built in space.
The engineering that's gone into the International Space Station, it is phenomenal, and it's a huge privilege to be part of that.
Engineering that's out of this world.
To get to see this amazing invention fly to the International Space Station is the most incredible thing I could possibly hope for.
And the pioneering historic innovations.
Oh my God, it's actually flying!
Normally, you'd never be able to come here, and this is a beautiful view of Paris.
That made the impossible possible. Space exploration is entering a new era. After decades of innovation, aerospace engineers are preparing to send the first astronauts to Mars and beyond. What they find may provide the key to colonizing the galaxy. And central to making this possible, the International Space Station.
The International Space Station is hugely important in the future of human spaceflight and exploration. We have to master a number of things so that we can go further into space.
For British astronaut Major Tim Peake, his first visit was career-defining.
I had a huge wow moment when you look and see it in all of its glory in the sunlight. It's a marvel of human engineering.
Orbiting the planet every 90 minutes, this $100 billion cosmic laboratory is the largest man-made object in space. Measuring over 100 meters end-to-end and weighing more than 400 tons, it has the same habitable space as a Boeing 747. Powered by over 3,000 square meters of solar arrays and producing its own air and water, the ISS can host 6 astronauts in a completely unique working environment. And the work that's carried out here has never been more crucial.
We're conducting research into how humans and robots interact. This is going to be very important moving forward for lunar missions and for our Martian missions.
So 5 plants from the top.
We're also growing food in space. We're trying to learn how can we make a closed life support cycle. This is the kind of research that's going to help us with those future space exploration missions.
But as research intensifies, so too must the journeys to the station. And back on Earth, aerospace engineers like John Curry are facing a problem.
The space shuttle was retired in 2011, and when we lost the space shuttle capability, we lost a huge amount of capability to service the space station.
To make the journey, astronauts must now travel to Kazakhstan for a pricey seat on board the Russian Soyuz rocket. To find a cost-effective solution, NASA are turning to the private spaceflight industry. And all of the companies involved share one vision.
Reusability of hardware can play a really important role in trying to reduce the cost and improve access to space.
So how do you build an inexpensive, reusable spacecraft? To find the answer, engineers will have to look to the innovators of the past. Space historian Amy Shearer Teitel has come to Edwards Air Force Base, deep in California's Mojave Desert, to discover a piece of engineering that seemingly defies the laws of physics.
Oh, wow. Okay, this is awesome.
Nicknamed the Flying Bathtub, the M2F1 was a prototype plane built in 1963 to overcome a particular problem.
If you look at it, it doesn't look like it should be able to fly, but in reality, it actually pioneered a whole new way of flying. The engineering behind this thing is actually pretty genius.
This unusual aircraft was the brainchild of American engineer Dale Reed. Because of the high cost of disposable capsules, NASA was looking for a reusable vehicle that could land on a runway. The problem was, the wings of traditional craft couldn't stand the heat of re-entry.
So engineers had to completely rip up the aerodynamics handbook and start again.
The shape of a conventional wing is what gives an aircraft its lift. As air flows over the curved top, it speeds up, creating an area of low pressure, whilst airflow underneath remains constant. This pressure difference between the two airflows produces lift. Reed's design got rid of the wings altogether and relied on the turbulent airflow underneath the body to generate lift. And in April 1963, his prototype lifting body design was ready for testing.
Now, because the M2F1 didn't have any motor, he had to find an alternate power source. And so he asked his friend Walter Whitey Whiteside, who was a hot rod enthusiast, to get him one of these. A Pontiac Catalina. The plan was to tow the lifting body behind the car to see if it would actually generate lift. So even though the vehicle itself doesn't have wings, Reed hoped that because the body is shaped like a wing, it would fly under the same principles. But success was far from certain, and that's what we're going to test right now, towing our model behind a car to see if it will really fly.
On the morning of the test, the M2F1 was towed across a dry lake bed with pilot Milton Thompson at the controls.
All right, we're rolling, and it's rolling, and that's exciting. It looks like it's trying to nose up ever so slightly. Oh, come on, come on! It looks like it might get off the ground. It's flying! Oh my God, it's actually flying! I can't believe it actually got off the ground.
Just like the model, Reed's test was a success. As the M2F1 reached 86 miles per hour, it lifted off the ground. Although only by a small amount, the theory stood up to the test.
So in the end, the lifting body design proved to really be a pretty incredible piece of engineering.
John Curry and his team at the Sierra Nevada Corporation in Colorado are taking Reed's concept to the next level.
This design is one of the most incredible pieces of engineering I've ever been lucky enough to be part of. It is going to change the world of space transportation.
The all-new Dream Chaser is at the vanguard of spacecraft design. Built in two configurations, this reusable lifting body spaceplane will carry both cargo and up to 7 crew to the space station. To make the journey, it will launch on an Atlas V rocket, but in space, it will make the 2-day voyage to the ISS using its own propulsion.
In orbit, when we're needing to fly, we don't have air. So we use our thrusters to get us there. Nitrous and propane, 22 of them, that can both orient the vehicle and can actually push the vehicle through space. Wonderful capability.
Once docked, Dream Chaser has the power to move the space station to help it maintain the correct orbit. But it's the return journey into Earth's atmosphere where Reed's lifting body concept will emphatically prove its worth.
When you start in space, you're moving at 17,500 miles an hour. As you go through the atmosphere now, The Dream Chaser then is able to take that 17,000 miles per hour and absorb all that heat that the atmosphere creates onto the shape and protect the cargo and the crew inside the vehicle. And the wings here, they're just on the edges and they're just providing the control like sails on a sail ship, whereas all the lift is being provided by the body itself.
And in October 2013, that theory is put into practice. A series of drop tests are conducted high above the California desert.
3, 2, 1, release, release, release.
Proving its aerodynamic qualities once and for all. When it returns from its first mission in 2020, this new space plane will touch down using a unique nose skid landing system.
The great thing about the lifting body design is it does so well at the high altitudes and then also does well at the low altitudes, such that we can touch down at about 200 miles an hour and then roll out to a wheel stop on any conventional runway.
Because of its design capabilities, each Dream Chaser will be used for at least 15 missions.
The opportunity for us to get to see this amazing invention fly into space to the International Space Station and back again is the most incredible thing I could possibly hope for.
But to ensure regular, cost-effective missions, NASA need more than one type of spacecraft. And to design them, engineers will need to look to the trailblazing innovators of the past.
It looks like it could potentially break his neck.
To produce more impossible engineering. The International Space Station travels in low Earth orbit 400 kilometers above the planet. Moving at over 17,000 miles per hour, orbiting the world every 90 minutes, this cosmic laboratory is providing scientists with a staging post for deep space exploration. For astronaut Major Tim Peake, getting there is the journey of a lifetime.
Liftoff of Tim Koper, Yuri Malenchenko, and Timothy Peake.
That 8-minute, 48-second ride into space is just the most thrilling ride you could possibly imagine.
With demand for travel to the station ever increasing, developing a fleet of reusable spacecraft is essential. And aircraft manufacturer Boeing is rising to the challenge.
This is going to be incredibly difficult. So not only do we have to design a vehicle that can take the loads experienced on launch, the high temperatures on orbit, the high temperatures in re-entry, and the impacts on landing, we're going to have to refurbish it, turn it around, recertify it, and then fly it all over again.
Aerospace engineer Melanie Weber is part of the team designing the company's first reusable space capsule.
The Boeing CST-100 Starliner is a space transportation system which is comprised of a pressurized crew module and a service module.
Underpinned by decades of NASA research, the Starliner has one incredible design change. Unlike all previous capsules that have landed in the water, it will be the first US crew module to land on solid ground.
In the past, water landings were favored because we had a lot of ocean out there to land on, and the water was good at attenuating the impact, but unfortunately it's not really good at reusability of a vehicle. Landing on land, of course, presents a unique set of challenges, and there's been a lot of analysis and models that we've had to go through. There is no second chances when it comes to landing on land.
So how do you design a module that can survive a ground impact after traveling from space? To attempt this feat, engineers need to look to the innovators of the past. Once upon a time, crashing wasn't really a problem, as everything moved so slowly.
Oh, terribly sorry, old chap. Not at all, old bean.
But as transport became faster,
Yee-haw!
accidents became more dangerous.
Consign it!
However, it wasn't until the invention of the motor car
Yoo-hoo! Hey, girls!
that safety was taken seriously. And in 1959, Swedish inventor Nils Bohlin released the patent for the three-point safety belt that we know today. But as the motor car really took off, it became clear that more was needed. At the Thatcham Vehicle Test Centre in the south of England, physicist Susie Shee is investigating how the need for car safety inspired some smart engineering.
We're about to run a test, simulating a frontal impact, as if this rig was being hit from the front, exerting a force of 16 Gs on our dummy friend here.
Unlike historical methods of crash testing, instead of moving towards an object, when activated, the pneumatically powered sled will fire the car backwards, replicating the forces of a head-on impact at 31 miles per hour in just 125 milliseconds.
Do you think he knows what's coming?
3, 2, 1.
That went so fast! Almost gave me a heart attack.
Playing the footage back in slow motion reveals the true force of the collision.
So I can see him sliding forwards really violently towards the dash. It's quite disturbing. Oh, his head's come all the way down, craning his neck. Okay, that looks painful. It looks like it could potentially break his neck.
Early attempts to solve this possibly fatal problem produced a dashboard airbag, but it had little success, rapid inflation being the main hurdle. But in 1968, explosives expert Alan Breed found a solution.
Breed realised that an explosion could create a lot of gas really quickly. So what he used was a trigger sensor and a compound called sodium azide, which releases a lot of nitrogen really quickly when it's heated. And that was all packed in to a section in the centre of the steering wheel. But that didn't solve all the problems of the airbag. This is the problem that Breed had to overcome. This roasting bag here represents my airbag. So if I squeeze it, rather than being soft, the air pressure inside means it's actually quite hard. And rather than absorbing the impact of the crash, you would just bounce straight back off it, which will potentially make the injuries much worse. What Alan Breed came up with was a system of vents specially designed to let gas escape after it had been inflated. So if I cut some vent holes in this one, this time the bag deflates slowly, cushioning the blow and absorbing the impact. It's a simple but ingenious solution to the problem.
To demonstrate the brilliance of Breed's design, the test is being run again.
I feel nervous.
But this time, the car has been fitted with a modern airbag system.
Oh my goodness! So the bag's definitely gone off. Actually, let's see if we can find the vents around here. Yeah, so here's the vents that actually let the gas out again.
And in slow motion, the genius of Breed's concept is even clearer.
Just there, just before he hit the bag, it was actually already deflating because the vents in the side are designed to release just the right amount of gas and then start deflating so that as he hits it, the gas will actually escape. So this is the problem that Breed had to overcome. This is the problem that Breed had to overcome. So this is the problem that Breed had to overcome. So this is the problem that Breed had to overcome. So this is the problem that Breed had to overcome. So this is the problem that Breed had to overcome. So this is the problem that Breed had to overcome. So this is the problem that Breed had to overcome. So this is the problem that Breed had to overcome. So this is the problem that Breed had to overcome. So this is the problem that Breed had to overcome. So this is the problem that Breed had to overcome. So this is the problem that Breed had to overcome. So this is the problem that Breed had to overcome. So this is the problem that Breed had to overcome. So this is the problem that Breed had to overcome. So this is the problem that Breed had to overcome. So this is the problem that Breed had to overcome. So this is the problem that Breed had to overcome. So this is the problem that Breed had to overcome. So this is the problem that Breed had to overcome. So this is the problem that Breed had to overcome. So this is the problem that Breed had to overcome. So this is the problem The deflation is absorbing the impact of the crash.
It's estimated this incredible innovation has so far saved the lives of over 40,000 people in the USA alone. Boeing engineers have taken the principle of the car airbag and supersized it.
What we have in front here is a flight-like, full-scale outer airbag assembly. As we're re-entering the atmosphere, we'll be going supersonic, and the parachutes will decelerate us to about 10 to 30 miles per hour on landing.
And that's where the cushioning system comes into play. Positioned underneath the capsule's heat shield, the 6 giant airbags are inflated as the capsule drifts back down to Earth.
They are filled using a series of high-pressurized gas bottles that are flowed into the airbag assemblies through a series of manifolds and valves.
And just like Breed's car airbag innovation, ensuring the vent size is correct is crucial to a safe landing.
As we land, the airbags will cushion the vehicle and vents will open up to allow the gas in the airbags to escape. That's important because if they didn't escape, these bags would be rigid and you could actually bounce off upon landing.
Although it may seem like an abrupt landing, the system cushions the capsule so well, each Starliner will be able to make the 400-kilometer journey to the ISS up to 10 times.
In my opinion, the airbag inflation system is one of the most unique engineering marvels to come out of spaceflight.
Providing cost-effective travel to the space station is one challenge. Maintaining its structure once there is quite another, which requires more help from history's innovators.
In many ways, the technology I'm using right now is exactly the same technology as divers would have used about 150 years ago when they were first starting to explore the seafloor.
To create more impossible engineering. The International Space Station, the largest cosmic laboratory ever built and a hotbed of cutting-edge research.
The work on board the space station is really focused on doing as much science as possible. In any 6-month period, we will conduct about 250 to 300 experiments on board the space station.
Orbiting the Earth for almost 2 decades, this monumental piece of space hardware is the proving ground for all future space technology. For NASA project manager Rajiv Dasgupta, that means focusing on a very specific challenge.
Eventually, when we go to Moon or the Mars, we will need long-duration habitats for the astronauts to live.
Habitation modules like those on ISS are 8x4 meter high-grade aluminium delivered via the space shuttle. But as the emerging fleet of new space vehicles have a fraction of the shuttle's capacity, engineers have come up with a mind-boggling solution. Expandable modules.
What you see is a full-scale mock-up of the Bigelow expandable activity module. The main advantage of an expandable module is to provide a permanent habitation system, but could be launched at a fraction of its final volume. Right now, this module is on the International Space Station.
Packed for launch, this module measures just 2.4 meters in diameter. But once inflated, its internal habitable volume is 16 cubic meters. Composed of 2 metal bulkheads and multiple layers of fabric, including Kevlar-like material, which is used in bulletproof vests, it's designed to withstand both internal pressure and survive the extremes of space.
When you put air in there, it'll expand and expand and expand, but it won't burst. That exactly happens because the Kevlar-like structural restraint is present, because it's taking the loads that resists the action to burst.
In April 2016, Beam is delivered to the space station to begin a 2-year trial. After berthing, it's inflated by using air from inside the station. Once it's reached full length, 8 tanks are then opened inside the module, filling it to its final pressure. For astronaut Major Tim Peake, it was a moment to remember.
The expanding process was very interesting to see. It actually sounded like popcorn going off. As slowly the air pressure expanded the module, breaking the small straps that were keeping it compacted.
Whilst on trial, astronauts will collect data and monitor Beam's performance.
Expandables can really revolutionize deep space habitats. It seems strange that fabrics will offer the structural capability as a metal module, but in fact they do. And the Kevlar or Kevlar-like restraint materials, they actually offer higher strength than aluminum on an equal weight basis. So because of that, the structural integrity of these expandable modules are extremely good.
As the station continues to grow in the harsh conditions of space, maintaining its structural integrity is vital for it to survive.
When you think about how the space station started and the demanding, harsh environment of the vacuum, the thermal extremes, the radiation, the micrometeorites, it's a truly remarkable feat of engineering.
As remarkable as it is, the extreme environment poses a constant threat.
There's plenty of evidence of the space station being struck by space debris. You can see chips in the window, for example, in the cupola window. One of them has a significant chip in it caused by space debris.
With the chip made by an object no bigger than a fleck of paint, ISS is vulnerable to damage from the smallest particles. And to carry out repairs, astronauts must perform regular spacewalks.
It's not a place people were meant to be. It takes hardware to be in space.
To enter an environment so completely alien to human life requires some extremely complex engineering. Aerospace engineer Rob Boyle is well aware of the challenges.
The spacesuit has to allow you to locomote around the spacecraft. It has to provide pressure. It has to keep you thermally comfortable. And it has to allow you to communicate with your other crew members. So every subsystem you think of in a normal spacecraft exists in a spacesuit.
One of the most complex problems is how to provide astronauts with enough oxygen over a long period outside the station.
You need an enormous amount of air to do a 6-hour spacewalk with straight tankage. So since oxygen is such a critical resource in space, we want to use it as efficiently as possible.
So with oxygen in limited supply, how can engineers provide life support for astronauts on a 6 to 8 hour spacewalk? To find an answer, they call upon yet another great innovator from the past.
Wow, it's really amazing down here. I can see sharks, sea turtles, all sorts of sea life.
Engineer Luke Bisbee has come to an aquarium in Manchester in the UK to discover how science mastered the art of breathing underwater.
In many ways, the technology I'm using right now is exactly the same technology as divers would have used about 150 years ago when they were first starting to explore the seafloor. My air is being supplied through this tube at the side of my helmet. And the weight of this apparatus that's sitting on my shoulders is actually pushing me down onto the seafloor. Now, of course, there are limitations to this system. With the tube attached to my helmet, I can only go so far. And in this well-lit open tank, it's no problem. But in a confined space, it could be really problematic. The tube could get caught or snagged on something and could even break, and obviously that would spell disaster.
But in 1878, pioneering dive engineer Henry Fluess, who'd experienced these problems firsthand, came up with an ingenious solution. Drawing on his knowledge of chemistry and physiology, he built a device which had the potential to revolutionize breathing underwater.
When we breathe, we convert oxygen into carbon dioxide. But not all of the oxygen that we breathe in is converted. In fact, about 75% of that oxygen remains in the air that we exhale. Now, Fluess's idea was to recycle our breath, filtering out the carbon dioxide and topping up the oxygen.
The basic principle of his design can be seen on this Fluess-inspired breathing apparatus, once used by firefighters.
When they exhale, the gas would pass through this tube and down into the scrubber bag here. And this is where the carbon dioxide is removed. The gas would then pass up through this valve where the oxygen levels are topped up using this tank of oxygen that's on my back. And the air then passes into this chamber where it mixes before then passing back up to the mouthpiece to give the makeup air for the diver. And this is called a rebreather. And it allows divers to safely use all of the oxygen in the air rather than just a small proportion of it.
Fluess tried to interest the Royal Navy in his rebreather, but with little success. However, he would soon get the opportunity to prove its brilliance on the biggest engineering project of the day.
Now, this is a place that very few people get to see firsthand. I'm inside the Severn Tunnel underneath the Severn River. And this was a project of astronomical proportions when it was first conceived.
Begun in 1873, this rail tunnel, more than 4 miles long, was designed to connect England and Wales. But soon, disaster struck when workers on the Welsh side hit an underground spring, flooding the works completely.
A series of watertight doors have been installed to isolate any serious leaks. But in the rush to escape the flood, the workers didn't manage to get them shut. Engineers couldn't begin pumping out the water without closing the doors.
Using a traditional surface-fed breathing system, one of the project's professional divers, Alexander Lambert, managed to get within 30 meters before his air hose snagged. Desperate for a solution, Fluess and his experimental system were summoned.
Using Fluess's rebreather was incredibly dangerous. It was largely untried, and Lambert had no idea how long he'd been under or how much oxygen he had remaining.
Lambert had to make the journey twice before he was successful, and spent a total of almost 3 hours underwater.
Today, the Great Spring is safely sealed behind the tunnel walls, but back then, Lambert had to force shut a heavy metal door in order for it to be contained.
With the tunnel secure, it could be pumped out and the work completed. One portable piece of engineering had made a record-breaking piece of engineering possible.
For 100 years, this remained the longest underwater tunnel anywhere in the world. And this incredible engineering achievement couldn't have been possible without Henry Fluess and his amazing rebreather.
Back at NASA, the team have used the engineering behind Fluess's invention to create a one-person spacecraft.
This is the NASA EMU, or Extravehicular Mobility Unit. It's what astronauts use on the International Space Station when they do a spacewalk. The NASA spacesuit has life support backpack, that's on the back. It has a helmet. The helmet has various visors and various sunscreens to allow use in all environments, dark or bright. The crew member has a display and control module. Here, this is where the crew member interfaces with the spacesuit.
Like Fluess's rebreather, the primary life support system worn on the back provides breathable air. A centrifugal fan draws exhaled breath into the unit. Carbon dioxide is filtered, humidity is removed, before more oxygen is added and fed back into the helmet. In all, a supplement of only 1.2 pounds of oxygen is needed for an 8-hour spacewalk.
The oxygen tankage, as far as efficiency in this suit, is very state-of-the-art. You can't build a smaller oxygen system that would provide what we need. It's an incredible piece of engineering.
And once inside, the EMU provides the perfect barrier between man and space.
The spacesuit's not the most comfortable thing to wear. You have to put the legs on first, and then you kind of have to get into the upper torso. It's a bit like a caving expedition. You have to go underneath it, both arms up, and then your arms come out. The most important thing, though, are the gloves. You've got to try and get as much dexterity in your fingers so that you can do the important work outside. To put that into perspective, we have 2 sizes of boot, but there are 47 sizes of glove. And that's how important they are.
Also crucial to maintaining dexterity is working at low pressure inside the suit. Before each spacewalk, astronauts must breathe pure oxygen for several hours, ridding their bodies of nitrogen that alters at low pressure. Once conditioned, they're ready to depressurize and go outside.
It feels very good to be part of the future of ISS and the future of spacewalks and the future of NASA. When you look at the advanced spacesuit teams, they come to us for state-of-the-art. They say, what are you guys doing and how can we adapt that to go back to the moon, to go to Mars, go wherever they want to go. It's fantastic to be part of it.
But being equipped with the most technically advanced spacesuit is only one part of the challenge. Taking the leap outside requires more inspiration from the trailblazing innovators of the past.
Wow, this is cool. A testament to the brilliance of the men and women involved in this incredible piece of engineering.
To create more impossible engineering. Constructed over 13 years, across 40 missions, the ISS is the largest man-made object in space. Consisting of 15 pressurized modules, including 3 laboratories, ISS has the internal volume of a 6-bedroom house. But not all of the astronauts' work is carried out inside.
Astronauts need to go outside the space station primarily to repair it and to do maintenance activity, but also to do science activity as well.
But leaving the station, as flight operations engineer Aaron Decker knows only too well, is far from straightforward.
You can imagine if you just opened up a hatch, all the atmosphere in the space station is going to go out into space. So we need the ability to break off just a small volume so the astronauts can go outside, and we don't waste all of the atmosphere that's in the rest of the space station.
So how do you maintain the pressure inside the station, but allow the astronauts to walk outside? The team at NASA need to call on another great innovator from the past.
This is amazing.
Physicist Andrew Steele has come to the top of the Eiffel Tower to discover the engineering secret behind this iconic marvel.
Wow, this is cool. Normally, you'd never be able to come here, and this is a beautiful view of Paris.
Built by renowned French engineer Gustave Eiffel and standing over 300 meters tall, the Eiffel Tower is one of the most well-known structures in the world.
But actually, although this is a great view of Paris, it's not what's up here that we're interested in looking at. Work on the tower's foundations began on the 28th of January 1887. And for the south and the east towers, the conditions of the ground were perfect.
Compact clay and gravel provided solid support, but the ground under the north and west towers nearest the River Seine was far from ideal.
The Seine caused Eiffel problems because it meant that the ground where the foundations were going to be dug on this side of the tower was waterlogged. If Eiffel's tower was going to get built, they'd need to find a way to dig through that waterlogged soil to the solid bedrock beneath.
To prevent water flooding his excavations, Eiffel turned to celebrated French mining engineer Jacques Triget. Working from earlier patents, Triget had designed a cunning pressurized tube system that stopped groundwater flooding a working mine shaft.
So imagine that this tank represents that waterlogged ground. Obviously we can see it's not really working out very well here for our little worker Claude. So what we need is this thing, which represents Triget's tube. And just pop that into the water there. It's got a little hole in the bottom which he can poke through, but you can see so far, not much use, he's still very much under the water. So what we need to do is increase the pressure inside that bottle and force the water out. And I'm just going to do that by blowing. Oh, there we go. And as long as I keep my thumb safely over the end here, then that pressurised air stays in there and forces that water to stay outside the bottle. But we very quickly encounter a problem, because once he's finished with that pickaxe and wants to go home and have his dinner, how is he going to get out of this bottle? Well, let's imagine that he wants to come out of the tube. Then we open it up. Oh no, poor little guy. The water level just comes back up to where it was, and I think he's drowned. So obviously what we need is some kind of mechanism that can allow him to leave that chamber without changing the pressure. That thing was called a pressure box, and these days we'd call it an airlock.
To leave the working chamber, the central chamber was pressurized to the same atmosphere. Workers then entered the central chamber, which was gradually depressurized to normal atmosphere. They could then open a second door leading outside. To enter, the process was simply reversed. Triget's revolutionary metal boxes, or pneumatic caissons, worked at the Eiffel Tower with great success.
When they eventually hit the bedrock, about 22 metres down, they poured quick-drying cement into the holes and topped it off with limestone and layers of cut stone. When construction was completed, Eiffel had the names of 72 engineers, scientists and mathematicians who he thought had been essential to the success of the project engraved on the side of the tower. And one of those names is Jacques Triget, a testament to the brilliance of the men and women involved in this incredible piece of engineering.
At the Johnson Space Center in Houston, NASA engineers have given Triget's airlocks a 21st century makeover.
This is the Joint Airlock module on the International Space Station. This module gives us the ability to go out and do a spacewalk.
Measuring over 5 meters long and 4 meters wide, the airlock is the astronauts' doorway into the vacuum of space.
So in here, we're looking at the equipment lock. So this is the volume where the astronauts will suit up, and then when they're finished getting ready, they'll go into this volume here, which is the crew lock. And then we close this hatch. And that allows us to depressurize the crew lock portion to vacuum. When the astronauts step outside and perform a spacewalk for the first time, it's an outstanding feeling, because we've spent months, sometimes years, training these crew members, and we've seen them from beginners work all the way up to becoming experts, and it's just a great feeling.
It's a feeling Tim Peake is familiar with.
For a rookie spacewalker, it's probably the moment of most apprehension, when you know that you're losing all the air from the space around you. And for me, when Tim Copra then opened the hatch and the sunlight kind of flooded in, that was the best moment, because I was so ready to go outside and get to work and start this spacewalk. It was wonderful.
Let's watch the set of lines as you come out. Yeah.
And once outside, it was worth the wait.
All right, gentlemen, looking great. Glad to see you both out there together on the tip of the world. Spectacular.
Every spacewalker gets a few minutes just to adapt to that new environment at the beginning of a spacewalk.
All safety covers look clear.
Great news, thanks, Tim.
For me, that was a wonderful opportunity, just to look down at planet Earth, and that was just wonderful to be able to see that.
The International Space Station is mankind's gateway to the rest of the universe.
The engineering that's gone into the International Space Station, it is phenomenal. Our future in terms of humanity's exploration of the solar system, for me, is very important. And the space station is going to help us take those next stepping stones.
And supporting those steps are some of the brightest minds in aerospace engineering.
I'm extremely excited to be a part of this. It's something that I've lived my whole life for. I love being part of human space exploration.
By drawing on the innovations of the past, adapting them, improving them, and making discoveries of their own, these groundbreaking engineers are making the impossible possible.
Whilst on the ground there can be differences between the nations involved, it seems that in space we have a great example of how we all work together towards a common goal. And it's a huge privilege to be part of that.